Okay, so now that we have talked about the dot product, now we can come into the cross product, which is a little bit different. But if you've ever learned anything about matrices when you took pre-calculus somewhere, then you'll recognize some determinants and everything um, from matrices. So many applications in physics, engineering, and geometry involve finding a vector in space that is orthogonal to two given vectors. In this section, we're going to study a product that will yield such a vector. It is called the cross product, and it is most commonly defined and calculated using the standard unit vector form. Because the cross product yields a vector, it is also called a vector product. So cross product, vector product, they pretty much mean the same thing in essence. So the definition of a cross product of two vectors in space. So if we let u equal u1i plus u2j plus u3k, and v equals v1i plus v2j plus v3k, be any vectors in space, then the cross product of u and v is the vector u cross v equals u2 v3 minus u3 v2 times I minus u1 v3 minus u3 v1 j plus u1 v2 minus u2 v1k. How in the world did we get to those? Well, easiest way to explain it is using cofactor expansion that we're going to describe shortly, as in right here. So a convenient way to calculate u cross v is to use the following determinant form with cofactor expansion below. Now, there are some things that we have to keep in mind. The top row is always our I, J, and K. The second row is always U1, U2, U3, so it's your first vector, just the components of it. The third row is our second vector, V1, V2, V3, just the components of it. The easy way to explain cofactor expansion, if you've never seen it before, is the following. So we're going to use our first row as our key. That's why we have right here, we have this I circled. So to do cofactor expansion, because we have a 3x3 matrix, we're trying to find the determinant of it. We're going to circle the I. We're going to cross out the row and column that it's in. By doing that, we're going to have our whatever we circled, which is our I, which is right here. Whatever's not crossed out becomes our new matrix of U2, U3, V2, V3, which is right here. Since we're using cofactor expansion, and I'm telling you to always use the very first row, we are always going to have a minus sign right here in between these two, in front of this J term, basically. So we got U1, U3, because we're doing this one now. We circle the J, we cross out the row and the column. We write what we have, U1, U3, V1, V3. So that's how we got to here. Next, we're going to do this one. We're going to circle the K. We're going to cross out the row and the column. We're going to be left with U1, U2, V1, V2 times K. Now, to find the cross product of anything, or no, sorry, not cross product, to find the determinant of a 2x2 matrix. So to think about our generic matrices. So if we had our matrix A, B, C, D, the lines on the outside mean it's a matrix, and we need to find its determinant, is really what that means. So the determinant of this matrix is AD minus BC. So that is how we're finding our determinant. And so that's how we're actually finding these parentheses right here in front of our I, J, and K. So since we're using cofactor expansion off of the first row, the J term always has a negative out front of the determinant. So notice here, right here, it says notice the minus sign in front of the J component. Each of the three 2x2 determinants can be evaluated using the following diagonal pattern, which is what I just found here. So here are a couple examples: 2, 4, 3, -1. So 2 times -1 minus 4 times 3. So -2 minus 12 is -14. 4 times 3 minus 0 times -6 is just 12 because this term goes to 0. So same thing, we're basically making this big ugly thing look into something easier and smaller. So we do have some properties of our cross product just like we do on anything else. So let U, V, and W be vectors in space, and let C be a scalar. So U cross V is the same as negative of V cross U. So it's not like our dot product. Dot product order didn't matter. Cross product order matters because when you start changing the orientation, we go from a positive to a negative. U cross V plus W would be U cross V plus U cross W. A scalar times a cross product would be C times the cross product of U cross V would be CU cross V or U cross CV. Just like before, you only bring it into one of them. If we have U cross 0, it's the same as 0 cross U, which is still 0 vector. U cross U is 0, so keep that in mind. Cross products with the same thing give us 0. Dot products did not. U dot, the cross product of V cross W, would be the same as U cross V dotted with W. So we can change a little bit of our orientation and still not have any issues. So some geometric properties of the cross product. So let U and V be non-zero vectors in space, and let theta be this angle between U and V. U cross V is orthogonal to both U and V. The magnitude of U cross V is equal to the magnitude of U times the magnitude of V times the sine of theta. Remember before for dot product, it was cosine. U cross V is equal to 0 if and only if U and V are scalar multiples of each other. Magnitude of U cross V is equal to the area of the parallelogram having U and V as adjacent sides. So these are some kind of geometric things that we want to kind of keep in mind and kind of start trying to visualize a little bit here. Because when you make it to Calculus 3, that has all this more 3D version in it, you're going to need a good basis for everything here. So if both U cross V and V cross U are perpendicular to the plane determined by U and V, one way to remember the orientations of the vectors UV and U cross V is to compare them with the unit vectors I, J, and K, which is equal to I cross J. That's shown in the figure. So the three vectors U, V, and U cross V form a right-hand system, whereas the three vectors U, V, and V cross U form a left-handed system. There is some good applications out there on YouTube and that you can Google that can show you easy ways to remember orientation. You're going to need that for Calculus 3 on determining if it's left hand, right hand, parallel, or perpendicular to your planes. So you may want to consider Googling some of that as well. So for vectors U, V, and W in space, the dot product of U and V cross W is U dot V cross W is called the triple scalar product as defined in the following theorem. So for U equal U1I plus U2J plus U3K, and V equals V1I plus V2J plus V3K, and W equals W1I plus W2J plus W3K, then the triple scalar product is given by U dot V cross W would be U1, U2, U3, V1, V2, V3, and W1, W2, W3. So basically what we're doing here is we're replacing the IJK piece of our cross product with the vector U of U1, U2, U3. We can still do cofactor expansion, except just now instead of having just a vector I, J, and K, we're actually going to have a value that we're going to multiply it by, which is U1, U2, U3. On a side note here for finding the determinant here of this matrix, U1, U2, U3, V1, V2, V3, and W1, W2, W3, you can Google more on cofactor expansion to see the form based off of what position you're in. If you wanted to expand it in a different way, in my opinion, the easiest and best way is always to expand it about that first row. That way you always know your signs are positive, negative, positive. So some geometric property of the triple scalar, the volume V of a parallelipiped with vectors U, V, and W as adjacent edges is given by V equals the determinant of U dot V cross W. So just like we've been doing before, just now this is talking about in a slightly different geometric way of doing things. So a natural consequence of theorem 1110 is that the volume of the parallelipiped is 0 if and only if the three vectors are coplanar. And what we're meaning by coplanar is that they're in the same plane. So that is if the vectors U equals U1, U2, U3, and V equals V1, V2, V3, and W equals W1, W2, W3 have the same initial point, they lie in the same plane if and only if U dot the cross product of V and W is equal to 0. So if you get 0, then we know that they have the same initial point and they are actually in the same exact plane. So we are told, find the area of the parallelogram whose vertices are -2, 2, 2, -2, 4, 4, -6, 10, -8, -6, 8, -10. So the first thing we actually have to find is we actually got to find V and W first to be able to see what we're actually doing here. So V is going to be P1, P2, which would be the vector -2 minus -2, 4 minus 2, 4 minus 2, which is the vector 0, 2, 2. W is P3, P4. I'm sorry, that's not right. It will be P1, P4, because parallelogram, we need the same exact point to get over there to it. So therefore, it's going to be the vector -6 minus -2. It's going to be 8 minus 2 and -10 minus 2, which gives us the vector -4, 6, -12. So then the area of the parallelogram of V and W as adjacent sides is defined as our area is equal to the magnitude of V cross W. So we need to find V cross W first. So that's our I, our J, and our K. We have 0, 2, 2, and we have -4, 6, -12. So this is going to be 2, 2, 6, -12 times I minus 0, 2, -4, -12 times J plus 0, 2, negative 4, 6 times k, which is 2 times negative 12 minus 6 times 2 times I minus 0 times negative 12 minus negative 4 times 2 times j plus 0 times 6 minus negative 4 times 2 times k. So when we simplify this, we get negative 36i minus 8j plus 8k. So therefore the area is equal to the magnitude of V cross W, which is equal to the square root of negative 36 squared plus negative 8 squared plus 8 squared, which, if my math is correct on this, would be the square root of 1,424, which is 4 on the square root of 89. So some of these problems are long, but they're not too hard in terms of the math. It's just a matter of figuring out exactly what we're doing. We had to figure out P1 to P2 and P1 to P4 in order to figure out how we can see what our vertices were if we were to try and graph this out and everything. So we're told let U equal negative 4i plus 3j minus 2k. V equals negative 2i plus 3j plus 2k, or 2, to find two unit vectors normal to the plane containing U and V. All right, so we're looking for, it says normal to the plane containing U and V. So in order for it to contain U and V, we need to find U cross V. So U cross V is negative 4, 3, negative 2, negative 2, 3, 2. So when we get to here, this will be 3, negative 2, 3, 2 times I minus negative 4, negative 2, negative 2, 2 times j plus negative 4, 3, negative 2, 3 times k. And when we simplify this out, we should get 12i plus 12j minus 6k. So now that we have our vector here, so it says the other such vector is V cross U, which is the same So we have the following. So we know that we have our U cross V. So U cross, this is our U cross V. Now, the other vector would be V cross U, which is actually the same thing as minus U cross V. So since a unit vector is needed, these vectors must be normalized. So the magnitude of U cross V is equal to the magnitude of V cross U, which is equal to the square root of 12 squared plus 12 squared plus negative 6 squared, which should give us 18. So the unit vector normal to the plane containing both u and v is going to be 1 over 18 times u cross v, which is 1 over 18 times the vector 12, 12, negative 6, or the vector 2/3, 2/3, negative 1/3. And then we also have 1 over 18 times v cross u. Oop. So that's going to be 1 over 18. So remember back up here, v cross u is just minus u cross v. So what that just means is we're going to change all of our entries. So therefore, that just means this is 1/18 times negative 12, negative 12, 6, which is the vector negative 2/3, negative 2/3, 1/3. So both of these vectors are normal to the plane that's going to contain u and v. So sometimes we got to kind of think about things in a slightly different way to understand that v cross u is just the same as minus of u cross v and everything. So we're just going to change and make them negative, all of the elements. So for our last example in this section, let u equal 6i plus 2j minus 5k, and v equals negative 6i plus 6j minus 4k. So that way when we go through and we're going to find our cross product here. So the only difference in our cross product that we're going to see here is that, so for u cross negative v, so this is going to be our I, our j, and our k. Our u stays the same, 6, 2, negative 5. Now we're going to have negative v, so that means we're going to have 6, negative 6, and 4, because negative v is 6i minus 6j plus 4k would be our values here. So we're going to find our cross product just like before. So this is going to be 2, negative 5, negative 6, 4 times I minus 6, negative 5, 6, 4 times j plus 6, 2, 6, negative 6 times k. When we simplify this, we get 8 minus 30, so negative 22i. 24 plus 30 is 54, so minus 54j. Minus 36 minus 12 is minus 48. Okay, so this would be our cross product of u cross negative v.